making sure that. Okay, good. Okay, I said last time that ANOVA source table is really, this is the most important part of an ANOVA, because you may not do the calculations in between, but you will need, you most certainly know how to run it at one point in time. If you do something that has to do with science, you will need to know how to run an ANOVA, some software. If you never have to run it, and you're lucky you have a statistician who does it for you, I think at the very least you should understand what the source table is. And that's really what's important. So you basically have on the source table, you have your different categories. You have your between groups variance, you have the sum of squares, you have your degrees of freedom, you have your mean squares, which is basically this divided by this. Then you have your F, which is the ratio between groups over within groups and over. Yes, variance. Then you have the corresponding p-value, which comes from a unimodal right-skewed F distribution with a critical value corresponding with your respective degrees of freedom in the numerator as well as in the denominator. If it exceeds, you have this little type 1 error risk left. That is your p-value. So that F score here corresponds with your p-value. Good. So that's the source table. Just make sure you know all the components of there. Degrees of freedom between the groups. Here you have society. This is 4 groups, -1 is 3. The residuals, this is your within groups variability. You have 3, 3, 3, and 4. That's 9 and 13 minus the groups gets you to your degrees of freedom within. So that's the between groups. That's the simple form of analyzing this. With the within groups, it's still simple, but it's also important to keep in mind that you understand what you need to enter to get to a successful within groups ANOVA. You have, this is where R statics, the package R statics comes into play, because that allows you to do an ANOVA test function, which allows you to within groups ANOVA. So you have a dependent variable, BV rating. You have within, it's the beer type. And you have WID, that's the ID, participant ID. This participant, because each participant has an individual number. And this refers to the data, DF2, which is your data frame. So once you run line 44, that actually takes a little longer because it requires more processing time because the calculation is a little bit more complicated. And then let's get ANOVA table, ANOVA 2, which is our beer drink example. This gets you to actually the within groups ANOVA. This gets you essentially to a source table, which is smaller than the one that we computed, but basically you have no degrees of freedom with 3 beers. It's 2. We have degrees of freedom in total. We have 8, which is essentially total degrees of freedom minus the groups minus the subject. And then we have an F, which is consistent with the F we calculated in Excel, a corresponding P, and overall P. The overall P is basically an overall summarization of the ANOVA, but the comparison between beer is basically significant, just like we see in the scene. So that's the ANOVA table for within groups. Then we talked about the post hoc testing. We talked about Tucky honest significant difference test. That's the Tucky HSD. If you run a Tucky for ANOVA 1. Excuse me. Yes, I just ran line 49. Yeah. So Tucky honest significant test calculates you on SM, which is basically a standard error of the mean, almost, with square, which is the total variance divided by, no, it's the square root of total variance divided by the sample size minus one minus the number of groups minus 1. So it basically gets you a so-called Q. Calculates you a Q, which is basically mean 1 minus mean 2, or mean 1 versus mean 3, or mean 2 minus mean 3 divided by this Sn. Gets you to a Q, and this Q essentially will be read against the Q table and will allow for you to test each of these means that you have obtained from your different groups against each other with a quote-unquote different critical value. So you will be more stringent and more strict in rejecting the null hypothesis with the aim to minimize the risk of a type 1 error, which basically goes hand in hand with the pairwise t-test adjusted with a p adjusted for Ferroni, which is basically adjusting the p-value for the number of comparisons. As a consequence here, you get, so this is again our between groups and over. We're getting here a comparison between each respective group, and you need to look at this row versus column. So you follow the row all the way to the column. So this is this POS comparison. Industrial versus farming is this comparison. These are the respective adjusted p-values. And you will only accept everything that's smaller than 5%. But these are adjusted for the number of comparisons in your analysis. So the only one that is truly significant here is natural resources versus foraging, natural resources versus farming. So that's how you approach post hoc testing. After you did the ANOVA, there are two situations where you do post hoc testing. One is if your overall ANOVA was significant. As we remember, for our ANOVA 1, this was significant, so we do post hoc testing. So if you, so the way you would report this essentially in, let's say, a paper, you would first do the ANOVA, you present the ANOVA source table, and then you basically go on with the pairwise t-testing, and in the second line you say, okay, in post hoc testing, only these two groups actually were significant. So first ANOVA source table, then post hoc testing. The same you can do with a pairwise t-test when you have a within groups ANOVA, and this is the comparison between cheap, mid-range, high-end peers, so no difference between cheap and mid-range, borderline significant difference between cheap and high-end, but quite a difference between high-end and mid-range. That's the post hoc testing, and that's the respective p-value. Same principle applies. You first have the ANOVA table, ANOVA source table, then the post hoc testing, and there you report the means and the standard deviation, or the means and the variance, or mean or whatever mark of variability you want to present, and a p-value that indicates that this was significant in pairwise comparisons after adjustment for Ferroni. So that was practice lab 4. And this essentially, as I told you in the beginning, the way I look at R is essentially, I want to show you these calculations in Excel because I think it's easier to explain these arithmetic associations of a statistical test and explain the concept by actually showing you that in Excel. But the R portion really means to show you how to do that in R. And the practice labs are some easy points to get, but it also serves the purpose that you have ran this code once in your lifetime. You may never do it again. If you do it again, you know where to find it. Good. Any questions about practice lab 4? If not, it's simple. You just run the entire code. Make sure that line 5 and 6 are hashtagged out. Run the entire code. Press Control L first. Run the entire code. Copy the entire code in a text document, which you get from the Spotlight. 5 and 6 hashtag out, click in the console, press Control and L. That clears the entire console. Then go into your script, press Command and A or Control and A on a Windows computer, which selects the entire script like this. Then you run the entire script with Control and Enter. And you copy them, everything in your console, and you copy it in a text file. And the text file is found in the Spotlight, or with a right click on a folder on Windows. Right click on folder, you go New and Text Document. Yes. Control E, and you have selected the entire script, then you run Control and Enter. Once you have the text file open, copy, create a new text document and copy this in a text document. Save this as STAT1021. STAT1021. Your family name, practice lab 4. That's your practice lab 4. 4 points. You're welcome. Good. 10 points. Did I say 4? Yeah. Oh, no, 10 points. Yes.
Sorry, scroll to the bottom.
That being the script, or that being the console? That being the console. The script.
Whatever you have to copy.
So that's the console, okay?
Yeah, I just want to make sure that mine's
P-value adjusted one for only. Yeah? All right, practice lab 4. Version accomplished. Now we're going back to our chapter 15. Okay, as promised, now we're moving forward. We're not doing hypothesis test. Well, we're still doing hypothesis testing, but we're not doing it in the scenario we have done it for the last classes. Because in the last classes, we compared a scale variable that was as a function of an independent categorical variable. That means we had a scale variable that was, what did we have? What were the examples? Wine rating. What was the other one? Absences in class or something like that. So we have a sample of a continuous variable, and the entries in your continuous variable are basically analyzed as a function of your independent variable with 2 levels. And these 2 levels could be in a paired sample t-test, before and after. In independent sample t-test, it's the nominal variable of the name of these groups. So if it's a randomized control trial, you have an intervention group and you have a control group. That's your independent variable. Is it control or is it intervention? So now we are with our next methodology. The next methodology compares now the relationship between a continuous variable with another continuous variable. So that means we have 2 scale variables. We have a scale dependent and a scale independent variable. That essentially is also the pathway into regression analysis, where regression analysis is the simplest method of predictive analytics. So you're basically predicting something. And we will do that with regression analysis. And if we're lucky, also today at the end of the class. So in essence, correlation is the covariation or correlation between 2 variables. So that means if you have one variable that changes, the other one changes too. It either changes by, if one variable increases, either the other variable increases as well, or it's the other way around. One variable increases, the other one decreases. One is called a positive correlation. The second one is called a negative correlation. Simple. So using this together, you basically can test for associations or correlation of these 2 variables, and you will find a lot of correlations. The only thing, and this cannot be said and written often enough, correlation is not causation. That means just because you find a correlation with something, that doesn't mean they're causally related. Not at all, actually. If you have a large sample size, basically everything correlates with everything. That's a problem. And to discern the correlations that are actually causally related or potentially causally related to those that are just spurious correlation because of the higher sample size, that's actually a lot of the work I do on a daily basis. And this is in epidemiology, we create causal pathways. And we try to understand with something that's labeled directed acyclic graphs, so-called DAGs. We're mapping out causal pathways, causal relationships to find out which ones are actually operative, which one are actually important. So correlation is not causation. That's important to keep in mind in this context. So the correlation is now, of course, there's calculation, of course, there's a number, and that number is describing the strength of this correlation. This correlation coefficient can be positive or negative, because as said, if one variable changes, increases, and the other one increases as well, this is a positive correlation. If one number increases and the other one decreases, that's a negative correlation. Logic, right? Therefore, the correlation coefficient can be positive or negative. What's important to understand that they have maximum. They can be maximally 1 plus 1, or maximally or minimally, numerically minimally, but in terms of strength, maximally minus 1. And that's where the catch is now. And this is, I'm flagging this, please don't make this mistake. The sign does not have anything to do with the strength. That means the strength increases either in a positive correlation, either with a larger correlation coefficient, so the larger it gets, the stronger it is, or in a negative correlation with its minimization. So the smaller it gets, the stronger the association. So minus 1, plus 1 are actually equally strong correlations. End of note, impossible to find. If somebody ever tells you about a correlation coefficient of 1 or minus 1, he or she's lying. Doesn't exist. Can't exist because essentially you will always have some variability that is caused. So if you have 2 data points, then you get a correlation coefficient of 1. But if you have a certain sample size that gives you like a realistic kind of estimate, it's virtually impossible. It is impossible to zero, because just measurement error will cause the correlation coefficient to deviate from a perfect correlation. Okay, so it is the strength that indicates how large it is. So basically you take the absolute value of that negative or positive correlation. That is the strength, only the strength. The direction indicates is indicated by the sign. So a positive correlation, where either the dependent variable is greater, the dependent variable is going to be. Remember, dependent variable y-axis, independent x-axis is now more important than ever. The example here, this is where again you need to actually put thought into whether this is a possibly causally related variable of correlation. So you have here the number of different words infants have heard determines the vocabulary size at age 2. So the way you would actually express this is that the vocabulary size at age 2 is analyzed as a function of the number of different words. Is different. So is this causally related? What do you think? Well, I wouldn't know where the infant or the toddler would have the words in any other means. So I think it's quite a classic example where you can assume this is a real relationship. It almost has to be. At least I don't have an idea how that could be different. But yeah, no, this is a positive correlation. So toddler at age 2 has a larger vocabulary size. It heard more words over time. Negative correlation. That's an MIT study. So essentially the proportion of homework copied determines the final exam grade. The more homework is copied, the lower the exam grade. Does that make sense? Yeah, I could see that. So basically, it's important to keep in mind final exam grade as a function of proportion of homework copied as a decreasing grade. Good. Inverse relations. Inverse relations, negative correlation. Basically, an increase in the independent variable causes a decrease in the dependent variable. Then we have talked about the perfect positive correlation. That's basically a straight line, and each point of your scatter plot would be located on this straight line. Again, this is probably the last one you will ever see. Then you have a perfect negative correlation, same scenario, the larger the x-axis of the independent variable, the smaller the dependent variable exam grade. So you have a decrease in exam grade with an increasing number of absences. That's also the example we will calculate today. So this correlation coefficient, we will get to how to calculate it in a second. So you have it's a maximal. It has a maximum of 1. So from 0 to 1 is a positive correlation. This convention also accounts for 0 to -1. So it's a strength. But in terms of the size or strength of the correlation, 0.1 to 0.3 is a small correlation, 0.3 to 0.5 is a medium correlation, medium size, medium strength correlation. Everything greater than 0.5 is a large correlation. Simple so far, right? Now the million-dollar question, which is a stronger correlation, 0.25 or -0.74? Exactly. It's the absolute value of a negative correlation that is determining the strength, so it's stronger than 0.25. Flagging this for the quiz exams. So that's a question you will almost certainly see. Okay, then you also, and we talked about correlation doesn't equal causation. Why does it not? Let's look at this correlation. So there's a 0.91 correlation between ice cream consumption and drowning deaths. Any thoughts on that? Does that correlation make sense? No. Why? So it's only that it's so high that bothers you? Okay. Yeah. Okay. What if I tell you that I think actually that's true? Yes, please. Bingo. Bingo. So it is that unknown third variable thing. It's this unknown factor that comes into play. So it's hard to say what the variable actually is. It could be the temperature in summer. It could be the ambient temperature. People just more likely to eat ice, and they're more likely to drown. It could be the time they spend in the swimming pool in summer. So there's some factor that basically associates and serves here in epidemiology. We would call it an instrumental variable. So this is this secondary factor that nobody thinks about that associates with your exposure. Exposure could then be ice cream. So summer ice cream, summer ice cream, summer time spent in pool, death. So basically that's how you would need to look at this. So yeah, so it's also it's a relationship in that direction that basically causes drowning, and it's not the other way around. So it's not that the grief of drowning causes us to eat more ice cream. Yeah, so that's I'm not sure I understand that chronologically, but that's a different question. So so these are spurious correlations that are basically caused by an unaccounted factor, by an additional separate factor that is not in your analysis, and that's to be kept in mind. So misleading or spurious correlations you find quite frequently, particularly with large sample sizes, and that's why it's important that you really understand every aspect and every factor in your correlations and in your associations in causal pathways. And this is such a directed acyclic graph. So you basically you have now, let's go back to our ice cream and drowning example. You basically the ice cream associates with drowning. Yeah. And it's, yeah. Okay, so you have A causes B, B causes A. So that's a possibility. You've got to move away from the ice cream example now. But basically you have an association in both directions. You cannot discern which one associates with which one. And then the problem is that this association could also be caused by a third variable that basically associates with both your exposure and your outcome. And that's the problem at hand. And the Pearson correlation coefficient is just a tool that will only quantify this association or this correlation. It doesn't help you on the pathway. It doesn't really help you to understand which one does really cause the other one. And that's really the problem. So in principle, the Pearson correlation coefficient is a statistic that quantifies a linear relationship between two scale variables. Also important in this context, it's linear, it's not nonlinear. It's symbolized by the italic letter R when it is a statistic based on sample data. So again, we have this distinction between sample data and population data. If you do a population health study, you will use the Greek letter rho for your correlation coefficient. An example for a population health study, you remember the happiness scores in different countries? That's where you would utilize a rho of study. I think that's the closest we've gotten in our examples, which would quantify as a population health study. So as a population parameter, it's rho, otherwise it's R. So how do you calculate R? So the Pearson correlation coefficient, this formula looks more complicated than it actually is, because essentially it has, like all the other equations we've looked at, it's basically a ratio. You have a numerator and a denominator. Let's focus on the numerator. So we know that both of our samples, so we have two variables. Variable one is, so we will work with the example of exam grades. So we have the example of exam grades as a function of absences in class. You would assume that somebody who misses class very often will likely have a worse exam grade. So absences and exam grade, variable X and variable Y. You have now for each of your variables, you have mean. You quantify here essentially the deviation of each individual entry from your NX. And you quantify the deviation of each individual Y from your NY. So you get a list of deviations. What you do next, you multiply those two. You multiply your deviations and you sum each individual product up. So this sum of products, what do you notice about it? We're still dealing with the deviations, so we're not squaring it. So it will preserve a negative sign. So if the sum of these products is negative, the numerator is going to be negative. So this calculation essentially determines in which direction your correlation will point, whether it's a positive correlation or a negative correlation. So, okay, so we're summing this up. Just think about it. When you have x minus mx, this is positive, and y minus my is negative. Positive and negative in a multiplication will become negative. If positive and positive becomes positive, negative and negative becomes positive again. You're dividing, so yeah, negative and negative will be positive again. You divide this now by the sum of squares, the product of sum of squares under the square root. That is going to be with no sign. That's going to drop the sum because the sum of squares by definition is square deviations summed up, multiplied by the sum of squares of y. So that will be positive. The square root doesn't change that. So you have now an R that is determined by a sum of products of your deviations divided by the square root of the product of sum of squares x multiplied by sum of square y. And that's as simple as it could be, essentially. It looks a little bit more complicated than it is, but we will calculate this in a second and it becomes clearer. Hypothesis testing and correlation is again follows the same outline as we essentially did for hypothesis testing with the set distribution and the t distribution. We identify our population, our distributions, make our assumptions, which are again normal distribution, random samples. We state the null research hypothesis, which is the null hypothesis would be that there's no linear relationship and that the dependent variable is not changing in a linear fashion. There's a change in the independent variable. Whereas the research hypothesis is that they do change in a linear fashion. They determine the characteristic errors distribution, which is the R score, but it basically follows a t distribution, as I will show you in a second. We determine critical values of cutoffs, which I will also show you in a second, and we calculate the test sets. We calculate our R. Based on that, make a decision. So, this being said, let's open the Excel spreadsheet, please. So we have now here our R formula. Just copying this in here. We have it here. We have now, and this is posted on your module. We have here an R table. The R table will show you the levels of significance for the two-test in a correlation. So what it essentially will be doing, it gives you a significant R value. So if you are interested in degree of freedom of, so we have 10 participants, we have 10 students that we're analyzing. We need, and this is the degrees of freedom in correlation a little bit are to be treated differently, because we essentially have now two variables. So remember that we're calculating the degrees of freedom, or the degrees of freedom are determined by the sum of squares, the underlying data for this calculation of the sum of squares, minus, and this is the one we're dropping, minus that one value that we don't need, because we have the sum of squares, we have all the data, we can drop one of these variables and can utilize this for this manipulation to get the t distribution closer to a normal distribution. So we are now dropping, missing a number here. We're dropping one of these associations, one of these numbers, and we get sample size minus 2 is essentially our degrees of freedom. And this is the degree of freedom we're using in our F-score, R-score table. Okay, our R-score table is essentially determined by the degrees of freedom. Degrees of freedom is n, the sample size, minus the number of variables. So this is 2 in a simple correlation. So 10 minus 2 is 8. 8 at the significance level of 5% corresponds here with an R-score of 0.632. 0.632 is our significant level. So if it exceeds 0.632, we know we have a significant correlation. Alternatively, we can also do this with the t-square table. It follows a t-distribution. That means if we have a degree of freedom of 8, we're basically looking at a two-tailed distribution with a p-value of 5%, type 1 error maximally acceptable, so-called alpha. We are accepting a t-score of 2.31. So if we're doing the calculation now, we're basically looking now at our two variables. With 10 students, disregard the student ID, that's just a unique identifier. We have 10 absences and 10 exam grades of the same students. First, whenever you do a correlation or regression analysis, always first do a scatter plot. So this is simply done by selecting both variables. Always keep in mind that the left variable is essentially your x. The second variable is your y. So we basically have exam grade as a function of absences in class. So for selecting this now, we can add chart elements. We know that we always want access titles. So we are relabeling this now as absences. Can you read that? Absences is a function. So this is unit count. Now we're clicking again on the same. We're doing another access title vertically. And this will now be our exam grade. Exam grade in percent. Good. So that's our data. What do we need next? Next, we need a mean. So we need an mx and my. This is simply calculated with the average function. The absences are quickly done. With 76 average of exam grade and with 3.4 as an average for the absences. Now next, we need our deviations. So that essentially, now let's actually do the squared deviation. So we do x minus mx squared, which is basically nothing else but this minus this logged in. Yep. The sum. So that's essentially our sum of squares x. X. Now we can just copy this whole thing. Copy this now. That's us to y minus my. Put it here and we change mx to my. Gets us our SSY. So this being said, we have now pretty much everything we need. Next we need is our product. So we need an x minus mx multiplied by my minus y minus my. So remember the calculation, remember the equation for this. So it's x minus mx multiplied by y minus my. We basically multiply this. This x absences minus mx that we need to log in. Parenthesis closed multiplied by y minus my logged in. Gets us now 10 different products. The sum of this consequence what we need. And now it's simple, right? Now it's super simple because now we just need to calculate our R by equal. This is the sum of our products. So that's F13 divided by the square root of this multiplied by this. So that's all that's needed. And that gives us our correlation coefficient of minus 0.85. And I will post a spreadsheet so you can go step by step through the calculations, but it's essentially it's super simple. So again, keep in mind the product, the sum of products here in the numerator determines the direction. The square root of the sum of squares x multiplied by sum of squares y, that basically gets us the variability into this equation. So the smaller the variability, the larger our strength, the larger our correlation coefficient. The wider the variability, the smaller your correlation coefficient, with the direction determined by your numerator. Makes sense, right? So alternatively, you can also use an Excel function here, obviously. So you have Corel will basically prompt you to enter array 1 and array 2. Array 1 is the X, array 2 is the Y. We're selecting absences 1 to 10. We select the exam grades 1 to 10. We present the same value as expected. Good. So this is now essentially the first correlation that we calculated. And this means now that there's a significant correlation between absences in class and an exam grade. So just as a little taste for regression next week, if you click now on this correlation and just click here on the data scatter, we go back now. Because the question, the logical question you're going to ask yourself now is like, okay, so there's a correlation, but what does that mean, right? So if you fit now a trend line through this, and you double click the trend line and you go here on the right, form a trend line, you select display equation and display R squared. So not only you get an R squared now, and the R squared we know already from ANOVA. The R squared is the effect size in the ANOVA. Remember to what extent basically the variability between the groups overlaps with the variability within the groups. That's the definition in ANOVA. So now we're basically using the R squared as the so-called proportionate reduction, the proportionate reduction of error. So that's the percentage of error in your data that is being explained by your model. So your model being here, that predictive line, because each of these lines, each of these points corresponds with a certain point on the y-axis, right? So you are explaining, you're predicting. So there's a certain error that your prediction has from the actual data point. That error lowers your R squared because you're explaining less and your error is larger and your prediction is not decreasing much of the error if there's a lot of variability. If it predicts it very nicely, then you have a very large R squared. So this is actually surprisingly large R squared. Of note, if you have a univariate analysis, like we have here, univariate means like it's one explanatory variable, you essentially can also take the, you can take the R, the correlation coefficient, and just square it. That's the same value. But that only works with, if you only do correlation or you have a regression with only one predictive variable. As soon as more than one, as we will do next on Monday, next class, we're going to do multivariable regression. Then this doesn't work anymore. Then the R square is calculated differently. So this is R and R square. Good. So how much does the strength of your correlation, how much does this actually matter? if you look at this formula, you actually can conclude on this formula, this is a normal linear function. That's nothing else but a function for a line, straight line. So basically you have a y, so n variable is a function of minus 5.4 times your x, which is each absence. You have a decrease of 5.4% of your grade. That's just, if you have no absence, that's your score. If you have been to class all the time, you have 92% exam grade. So that's how you interpret this. And this is where correlation is really brought to work, right? That's where it's getting really exciting. Good. So this is correlation. Any questions on that? There are per se. So again, so we have the sum of products. That's minus 304. And as you see, this is already negative. So that point already will be a negative R. So it needs to be a negative correlation. And then you're dividing it by the square root of the product between sum of square x and sum of square y, which you've calculated here. Yeah? Yes, you have a question?
Yeah, why would I want R squared?
At this point in time, not yet. On Monday, you will see why you need the R squared. Because the only thing that R does, and just to put this, so the null hypothesis of R is that there's no association between variable 1 and variable 2. So if variable 1 changes, variable 2 doesn't change. And that's essentially what so this is, let's try this. This is a perfect correlation, right? Logic. The null hypothesis, so this is significant, this is a significant correlation. Your null hypothesis is you're testing against this. You're testing against y being the mean of y. So this is the shape and form which your null hypothesis looks like. Basically, the null hypothesis of correlation is it's a flat line. So it's not only a flat line, there also could be a line like that. But what really gets you closer to R is like this 45 degrees angle. That is that correlation. Irrespective of, so this is equal balance between X and Y. So it basically describes this 45-degree angle. And that's what you're getting at arithmetically by multiplying essentially the deviation from the mean of y, deviation from the mean of x. This is what you're basically putting together. So you basically quantify only that slope, and then you put it together and you're dividing it by the variability. So this is the significance. This is the highest level. This is a quantification of the R. Not R squared. R squared does something different, but in the simple format of the univariate correlation analysis, it is achieved by just squaring it. Later, when on Monday, we do multivariable analysis, with each additional variable that you include in your model, you will basically increase the predictive quality of your model. And the R square will increase by adding more variables to it, because you explain more with each variable. So it changes in the way you're looking at your model. But yeah, in its simplest form, maybe I shouldn't have said that even because now it's confusing me. So yes. So for now, it's the R that basically just describes this correlation. The R square is just a continuation in the thought process of describing associations and the error within a scalar. But yeah, makes sense? Answers your question? Yes, out of the way. Okay, linear relationship. We're describing a linear relationship, as we said. We did the 6 steps. We did the scatter plot. We did calculate the correlation coefficient. You can correct the review my calculations, but correct. So this is basically what I need to say. That basically it subtracts a mean from each score and divides by some kind of variability, which is the product of the sum of squares. And by putting it in the denominator, it also factors in the sample size. Because because it affects the variability. Then you also have to consider partial correlation, because there are different correlations that are basically being at work. So there could be an association between 2 variables that is to a part determined by a third variable. And then you can basically attribute the weight of each of these correlations to over correlations. So if you have 3 variables, you can basically use correlation analysis to kind of find the respective weights in your prediction. The way you're looking at that is basically by, again, it could be an association with different variables. So you would have kind of independent correlation with the homework assignments. So you basically have different associations with percentage of completed homework, for example. That's the MIT example again. So you basically have a correlation with the longevity in years. So that's kind of how old you are. Then you have years of education. That is basically how long you have been in school, because the further you are in your academic career, the more likely you're going to be very serious about completing your homework assignments, and the weekly of hours of tennis you play, which is an inverse correlation that basically correlates it out. So essentially, all these 3 together build an explanatory kind of framework for the dependent variable of completed homework assignments. And some of these may intersect. That means that weekly hours of tennis may associate with the completed homework, but weekly hours of tennis also associates with longevity in years, because you may be more likely to play tennis when you're older. You may be more likely to play tennis when you're long in school. So this is basically where partial correlation needs to be considering overlapping variabilities and overlaps in their predicted qualities. This is displayed here in the so-called Venn diagram, where basically you have the probability, you have a certain estimate of longevity in years, second variable weekly hours of tennis, and the third variable years of education. So they are intersecting at some level, where you basically have common ground for both of these variables, and they're correlated. And only when they're coming together, you basically get a true estimate. And for a predictive model, for example, you would be interested only in B, where all of these 3 are intersecting, and you try to tease out all the other factors to only get that true estimate of B. So you're removing the effect of a confounder from the prediction. That's where partial correlation is really important to keep in mind. Lastly, last 3 minutes, also quickly talking about psychometrics. So psychometrics are used in the development of tests and measures. Tests being here surveys in particular, will basically use psychological tools to basically measure a metric that basically reflects some psychological associations. So that's where it's used most frequently. And this is actually, this is a real, especially a real discipline, it's psychometrics. So experts of psychometrics and sort of psychometricians. So they use correlation to examine 2 important aspects of development and measures, which are reliability and validity, that we have discussed already briefly with, for example, the Rorschach ink blots test in chapter 2, which essentially is a debatably reliable and debatably valid test. With validity, nobody knows how to basically estimate or characterize a personality based on a strict figure. It's hard to interpret and it's questionably valid. A reliable measure is a measure that basically, if you do it on day 1, it should be the same on day 3. So if you measure the height of somebody on day 1, and that height on day 3 is not the same anymore, you have a very questionable measure, right? So this is not a reliable measure. You can also, so this is test 3 test reliability. It means that day 1 is the same result, same insight on day 3. If you have a psychometric survey and you give an individual on day 1 that survey, and on day 3 he comes to a totally different result, again, questionable test 3 test reliability. Reliability can also be quantified with one cross-section assessment, where you take a survey, have somebody fill out that survey, and you do a so-called split half reliability. A split half reliability means that everything that survey tests is being valid and it is accurately captured by your test or survey questions. One way to test that is by basically taking, let's say, 100 questions in your survey. You take the odd questions, so the question with an odd number, and you take the question with an even number, and you basically split them in half, and you say like, okay, so I basically compare now the correlation between the odd and even responses, or grades, or points, or scores, and if they correlate, I know that my survey is internally valid, internally consistent, and consistently and reliably reflects one common outcome and the same kind of reliable estimate. Make sense? And of course, there's a metric to that, and that's the so-called coefficient Cronbach alpha. So that is used to estimate this reliability, or also called internal consistency, by basically doing exactly the split half correlations and basically correlating the split half correlations in a certain sample population with each other, and that's quantified as Cronbach's alpha. You can hypothetically, if you are quantifying that and you do a survey, Cronbach's alpha can take on a value between 0 and 1, and you would strive to have a Cronbach's alpha greater than 0.7. Opinions differ. I don't think the conventions are not as stringent as far as I know. A valid measure is basically something that measures something that it was indeed designed to measure, and correlation of such a measure. So let's say you have a survey that gives you an idea about the patient's health, and you try to find out whether the individual's health perception of his own health. Like if the question is like, if the question points out, how do I feel? How healthy do I feel? Which are surveys that exist. That's the quality of 5 surveys. And you are able to determine in a sample population that perception of health with the number of hospitalizations that the individual had over the last 6 months, and you find such a correlate, you know that your survey is measuring something that is clinically valid. And that's how you could establish validity, by correlating it with some clinical or some pre-existing knowledge about the sample population. Okay. Any questions on that? I know it's a little much information today. Then we have the validity of personality quizzes, and that's just the point that these psychometrics we just discussed, Vogue and Cosmopolitan, whatever journals and magazine, they don't do that. So essentially, these journal and magazine surveys are to be taken, but cautiously, and they're usually more like for fun with a coffee on a Sunday morning or something. It's not a psychometric assessment. Thank you very much. Have a nice evening.